Hi, I'm Mikko from Mosomic. A while back I was invited by the Marcus Wallenberg Laboratory for Sound and Vibration Research at the Royal Institute of Technology in Stockholm to give an online seminar on MEMS microphones. Of course, I was happy to get the invitation and I said yes. I called the seminar 20 years of MEMS microphones from 2001 to 2021. It included a brief look at the history of MEMS microphones from my personal point of view, having worked at Nokia and at Acoustica Bosch and now in my own company. I also took a look at the MEMS microphones now, what comes to performances, suppliers, trends and so on. The seminar took place on April 28, 2021. I hope you find it useful. Cheers!
Sorry, but I think the sound is a little bit faint.
That's because my microphone was away. Some
Great.
microphone talker. Is it better now?
Yes, definitely.
Great.
Thank you.
Okay, that was a great start for a microphone speech. Okay, so the topic of today is 20 years of MEMS microphones. I'll talk about the history of MEMS microphones, but I'll do that from my perspective, from my work history. So I'm not going to go back to the 80s, to the very first moments of MEMS microphone history. And after that, I'll take a look at the MEMS microphone landscape as it is now, the suppliers, the trends, the performance levels, and so on. Unfortunately, I realized yesterday that I don't have time to talk about MEMS microphones versus ECMs or normal scale microphones. By normal scale microphones, I mean regular microphones that most people think about when they think about microphones, the ones you use in studios and public address applications. So I'll have to save those for another session. First of all, let's take a look at my background. That will help you understand the history lesson also, maybe better. So I started at Nokia in '98 as a summer trainee, and then I did my master's thesis on directional microphones for mobile phones in 2001. And after that, I joined the so-called platform microphone team at Nokia. And the idea of that team was to provide microphones for almost all Nokia products. So it was sort of a company-wide microphone team for all phones that Nokia made. At the time, Nokia was at its biggest, and it was actually the biggest microphone buyer in the world. And that meant that about 3 billion microphones were used during the time that I was in the microphone team. And of course, that was a great learning experience for me to learn about consumer electronics, microphones, and also working with all the best microphone suppliers that were out there. So it was a great school for me. I didn't study any acoustics or hardly any acoustics at school, so I've learned mostly by doing. Then in 2011, Acoustica, a subsidiary of Bosch, approached me, and they wanted me to lead their product innovation activities as a part of their marketing organization. I took the offer and moved my family to Pittsburgh in the States. And also Acoustica was a great learning experience and a great opportunity to learn. The product development team at Acoustica was magnificent, and then there was the Bosch backing, and Bosch obviously is a huge MEMS house, and the amount of know-how was extraordinary. And in my role as the sort of forward-looking guy, I also, of course, talked with a lot of customers and partners and learned from them as well. In 2016, I returned back to Finland with my family to bring the kids back to school over here. And that's when I started Mosomic, this one-man consulting business that I'm still running. I've done consulting for microphone manufacturers, marketing projects, documentation, and so on. And I've also worked with microphone buyers, people who use microphones, given them general advice, help them with the implementation of microphones into their products, help them choose components and suppliers and manage those suppliers and so on. And the products have varied from mobile phones to smart speakers to sound pressure level meters, so quite a wide variety of systems. Again, a great way to learn, to interact with a lot of people and learn on the way. In 2019, I started releasing this MEMS microphone guide on YouTube. It's a series of 28 videos, more than 9 hours of content that I published on YouTube. That was sort of a way for me to market myself and gain visibility and hopefully some credibility too. And so far it seems like it's working well. So quite a lot of customers have found me through these videos. Then about a year ago, when things were sort of gonna be coming back to normal after the video project, Corona hit, and I thought, okay, what better time than Corona to write a book? So right now I'm turning the MEMS microphone guide contents into a book, and so it's that material and maybe 40-50% more stuff. So that's my history and where my expertise comes from. Okay, so let's look at the history. Like I said, this is from my point of view, not a comprehensive history. Back in 2001, when I joined the microphone team at Nokia, it was all ECMs, electret condenser microphones. And they were these 4 or 6 millimeter capsules, a little bit like you see here, except that the capsules used at Nokia, they used spring contacts instead of any kind of solder. And the microphone capsules were housed in plastic or rubber housings that looked something like my drawings here. So here's a capsule in the middle and then a rubber boot around it, and an access to the top of the microphone for sound, and then coil springs on the bottom to provide the electrical contacts to the circuit board. And another housing that was popular was this kind of plastic housing that included the acoustic channel that went all the way to the surface of the microphone, and again spring contacts. These spring contacts were one of the main reasons why there was a need to change. The reliability of these contacts was quite poor, and they were probably the biggest reliability concern in microphones there, and that was a reason to look for other kinds of solutions. So in 2003, MEMS microphones came into the picture. MEMS, of course, stands for microelectromechanical systems, and the first supplier that had components that seemed credible enough to be used in mobile phones was Knowles. They were the first company that had success with MEMS microphones, bigger success, and that was a big part of that was the Motorola Razr phone that was hugely popular, and it used Knowles microphones. Here you can see some pictures I found online of those components. So here are the whole components, and this is what it looked like inside. So there's the MEMS sensor, and then bond wires connecting it to the ASIC inside the component. And then back in those days, you still had these standalone capacitors for disturbance filtering. You don't see those much in microphones anymore, but then they were still parts of the components. At Nokia, we had a very strong reliability reputation to upkeep, so we were kind of cautious of diving into these new technologies. So the introduction of MEMS at Nokia was kind of slow compared to some other microphone users. We had some ways to mitigate and minimize risks related to microphones, and those included, of course, extensive testing, both reliability and performance. And another way was to do multi-sourcing, which means that we had one specification and multiple suppliers who made the components to that same specification. So if one supplier had problems, quality problems or problems supplying the components, then we could rely more on the other suppliers. So that brought us safety. That's why we came up with a standard spec, and the idea was to make it easier for Nokia to start using MEMS microphones, because in the beginning most MEMS microphones they had different housings and different specifications. So we wanted to create our own specification, which would hopefully then become a standard. So that's what we did. So there was one electroacoustic specification and two different mechanical specifications. One for a top port microphone, something like you see here on the top, and then a bottom port component, something like the one below. And the specification was for a digital interface. And that was another source of delay in the introduction of MEMS microphones and surface-mounted microphones at Nokia, because the suppliers had to develop also the digital interfaces into those components. And the reason for the digital interface was basically disturbance immunity. I think that was a great idea back then, and it still is. Especially in a device such as a smartphone or a mobile phone that may have half a dozen antennas and multiple microphones, the conditions are quite harsh, and a digital interface makes it much easier to achieve a better or a good signal quality, because digital interface is obviously much more immune to disturbances. We chose PDM as the interface type, and that was simply because PDM interface was already available in the phone systems at Nokia. So analog microphones were connected so that the signal went out to a mixed signal system, and from there as a PDM signal to a digital system. And when we started using digital microphones, they were just directly connected to the digital system. It was a plug and play connection, so no new interfaces needed to be added to the system. Then the first component that was made based on this 3x4x1 millimeter digital specification was actually a top port surface mount ECM. The supplier called it the MEMS killer. And even though it didn't quite live up to its name, it was still a very good component. And after some initial hiccups, it was a good component. There were initial hiccups with basically every component in the early days of SMT components we used, so this was nothing out of the ordinary. Those components didn't have a long lifetime or long career in Nokia phones because of two main reasons. The first one was that electret microphones tend to lose sensitivity in reflow. So these being surface-mounted components, this was obviously a problem and a source for inaccuracy in microphone sensitivities. And another problem was that bottom port components were more difficult to make as ECMs, so they were not available. So next we'll take a look at the first MEMS microphone that Nokia used. And actually this was not made according to the 3x4x1 specification. Instead, this was a really small 2.6 by 1.6 by 0.9 millimeter component, and the small size made it very attractive for us and some phone projects, and it was attractive enough so that we forgot about the multi-sourcing strategy that we were enforcing already then. And of course, we put these microphones through all the short and long-term reliability tests, and it was a good component until some problems were found, and they were related to condensation, and the end result was that there were disturbances in the components in some circumstances and conditions. So sadly, the component didn't have a long life in the Nokia phone lineup. Later on, the problems were fixed, but by then it was already too late for this component as a part of Nokia's component portfolio. So from these early problems, we learned a lot of things, and one key thing that came out of that was these use case tests. They are tests that simulate real-life devices and applications and use case, and look for things like performance reduction and disturbances and other problems in microphones. And the idea was to try to find problems before these microphones end up in any kinds of devices where the problem obviously then is bigger. Another lesson learned was that multi-sourcing was enforced then on after the Sonion component, which was a one-off component. We learned that especially with new technologies, it's not a good idea to go with just one component, especially when the device volumes are as huge as they were at Nokia. Then between about 2005 and 11, when I then left Nokia, we worked with pretty much every microphone manufacturer that had any kind of credible plans or components available. So the companies were Knowles, ST, ADI, NXP, Infineon, Wolfson, Acoustica, and so on. Of course, not all of these developments and cooperations resulted in any kind of a commercial cooperation, but anyway, I think we learned a lot by doing this, and I think the microphone suppliers learned a lot too. Of course, with new technologies and new components, there are always problems, and I've listed here some of the key ones that came to mind. And the first one here is low performance. The early MEMS microphones, their SNRs were below 60 dB, and there were also other performance drawbacks. So that was a challenge. Our target in the early specifications was 62 decibels SNR, and these components couldn't quite meet that. Then there were some components that just stopped working after being on the shelf in an office for a couple of months. Then there were contamination problems. I'll talk about this a little bit more later on. And problems related to condensation, like the one with the Sonion component. And stiction was one of the key issues that had to be resolved by all manufacturers. That means that in a capacitive sensor, you have a backplate and a membrane, and in some conditions, the membrane meets the backplate and sticks to it, and of course that kills the functionality of the component until the membrane is released from the backplate. And there were then all kinds of solutions to prevent this from happening. One other problem that we saw was that in bottom port components, where the sound hole is on the side where the solder contacts are, some of the solder ended up in the microphone sound port, and that was partly a component design issue and partly a manufacturing issue at the phone circuit board production line. And then there were all kinds of issues in the MEMS ASIC systems in those components. One of the key things was that the ASICs were not able to cope with all the signals that the MEMS chips put out. For example, there were these really low frequency signals that the MEMS put out in some conditions, and the ASICs were not able to handle those. And when I talk about low frequency, I mean like 1 hertz or even lower. So the whole electrical system had to be improved in the early components. And one more thing I want to mention is drop tests. Pretty much all MEMS microphones had some kinds of problems in drop tests early on, but there were some particular problems related to drop tests that also include a pressure shock when the test is done. So when a phone or some other device hits a ground so that the sound channel to the microphone hits the ground, then the air between the ground and the phone gets squeezed violently into the sound channel of the microphone, and it causes a pressure shock to the microphone, and some microphones were not able to tolerate that pressure shock. Okay, then let's look at what's happened to the market between about 2008 and now. So obviously the MEMS microphone market has grown strongly, and there are some main drivers for that. Obviously, MEMS has taken a lot of market share away from ECMs, so that has driven growth in the MEMS microphone market. And also the amount of devices that manufacturers are producing has increased, along with the fact that also the number of microphones per device has increased. So back in the early days of MEMS, there was basically only one microphone per phone, even in higher end phones. But nowadays, as we know, there are 2, 3, or even 4 microphones per phone. And another thing that has caused market growth in MEMS microphones is the speech user interfaces and arrays that are used to improve those interfaces. So there may be an array of, for example, 7 microphones in a system, like there is in the Amazon Echo, or at least one of the Echo products. So obviously, if you have 7 microphones per device, it's good for the MEMS manufacturers and for their business. So let's look at what has happened to the suppliers. There are some suppliers that have been acquired by other companies but are still in the game, and ADI is one of those companies. So they were bought by InvenSense, and then InvenSense was bought by TDK TDK, and then turned into TDK InvenSense. The ADI technology legacy still lives on at TDK, and TDK is putting out all kinds of components still. I put an example here of one of their products that they released not so long ago. And as far as I know, this is the first acoustically directional MEMS microphone. So there's a sound port on the top of the component, another one on the bottom. And this is a unique component that I wanted to mention. Other suppliers that have ceased to exist, or at least are being pretty quiet nowadays. Here's a list of them. So the first one is Sonion. They were bought by Pulse, and then they were bought by Epcos, and Epcos was bought by TDK. So now also the Sonion legacy lives on at TDK, and NXP was bought by Knowles, and Knowles was mostly interested in NXP's miniature speaker lineup. And since Knowles had their own microphones, the NXP lineup was terminated, which was kind of sad because they were pretty close to being ready for mass production, and the components were good. Another example is my former employer Acoustica, who were bought by Bosch in 2009. But sadly, things didn't go quite as well as they could have, and the doors were shut at Acoustica in, I think, 2018. Another company that we worked with in the early days was Wolfson. They were bought by Cirrus, and nowadays it seems like it's fairly quiet on the microphone front at Cirrus. I don't know exactly what's going on, but I haven't heard that there would have been any new announcements lately. The same goes for Omron, who used to supply MEMS sensors for ST. Then let's have a look at a couple of newcomers to the market. Sorry, I had one more comment here about the difficulty of developing MEMS microphones. Obviously, the list here of companies that have ceased to exist it's a clear indication for me, at least, that it's definitely not easy to develop a MEMS microphone and make it into a profitable business. So I think that's an interesting thing to note about MEMS microphones. So like I said, here are a couple of newcomers. Vesper, I don't know if you can call them a newcomer anymore. They've been around for a few years now. And what differentiates them from other MEMS suppliers is that their components are based on piezoelectric technologies instead of capacitive like all the others. Then one other company that's not yet selling their products but is developing a laser-based optical microphone system, and that's Sensible in Norway. The performance levels they're talking about are quite high, so it's going to be interesting to see what they come up with. So the market landscape. I'll go through this fairly quickly because time runs fast. So what comes to MEMS sensors, and now I'm talking about just the MEMS chips, not the whole packages. Two companies rule the market, and those are Infineon and Knowles. And according to the latest reports, it seems that Infineon might have even surpassed Knowles. Knowles has dominated the market since the early days of MEMS, but now it seems Infineon has caught up with them. Infineon sells most of their chips to other companies to package them and sell under their own brands, and those companies are, for example, AAC, Goertek, BSE, and so on. Knowles, they use most of their, or I think all of their chips themselves, so they package them and sell them under their own brand. Sony is another MEMS sensor manufacturer, but I don't think they've sold anything under their own brand. They're more like a foundry for Knowles. Then what comes to the complete MEMS microphone market? I have this market graph here. It's a bit outdated from 2 years ago, but it's still pretty much valid. So the main players are Knowles, AAC, and Goertek. And then there are companies like TDK Inventions and Infineon who concentrate on the higher end of the market, so higher performance components that may not be quite as cheap as the other components. Other notable suppliers of complete components are ST, BSE, and Vesper. Then let's take a look at what's happened to the performances and capabilities of MEMS microphones between 2005 and now. So like I said, in the early days, the SNRs of components were below 60, and over the years they've evolved, and there have been pretty big leaps in the performances of the best components in the last maybe 4 years. And now the components are up to 74 dB, which is a really good number. There are even talks about higher levels by Sensible, but like I said, those aren't available yet, so we'll see what happens. But they're talking about 80 dB, which is a really good number for a really small microphone. Acoustic overload point, back in 2005, it was somewhere between 110 and 120, and that's still good enough for many applications. But then there are some cases like the one we had at Nokia, that people were using their camera phones to take recordings at music concerts, and the picture quality was great because the cameras were evolving quickly, but the sound was horrible. So we came up with a couple of inventions, and this new product line or component line, Nokia Rich Recording, was the market name for it, and the AOP in those was 140 dB SPL. Those were really good components, and I'm a bit sad to see that they're no longer there available since the Nokia technologies were scrapped after Microsoft stopped producing phones. Nowadays, the AOPs are somewhere between 130, 135 for sort of mass market high-end components. And there are even components with AOPs up to 150 dB SPL by Vesper. And this, of course, is a really high level, and it rivals these bigger studio and public address microphones. So MEMS microphones don't really lose at all to bigger microphones in this category. Size, it started with roughly 5 by 4 millimeter components, and nowadays the standard for both analog and digital components is about 3.5 by 2.5. Components could be made smaller also, like we see here. There are components below 3 millimeters in length, but the thing is that when you minimize the size of a MEMS component, you also limit its performance. SNR and frequency response, for example, suffer if you make the component too small. So both microphone manufacturers and device manufacturers have preferred to keep the component size pretty much as it is and just try to improve the performance. Reliability in 2005, it was questionable, or in some cases very questionable, and now I would say it's good. I'll come back to this a little bit later. Let's look at performance trends for MEMS microphones. So at the moment, the SNR level that the mass market devices and components are going for is somewhere between 61 and 65 dB. Some higher end smartphones, they go for higher performances between 65 and 70 dB. There are also these higher than 70 dB SNR microphones available for high performance applications. For example, long distance speech UIs, like you see here in the picture, the guy talking to the smart speaker from a couple of meters away, conferencing and music recording. And there's also a need to add value to the components. So that's one more reason for microphone manufacturers to increase the performance levels. Acoustic overload point, like I said, 120 is okay for most, but higher sound pressure level capabilities are needed in difficult environments like loud concerts or sports activities, in windy conditions and in vehicles. And also in speech UIs that are in loud devices. So for example, smart speakers, they may blast loud content through the speakers, and the microphones in the same device pick up that sound. And as long as the sound is not saturated, it's much easier to remove that speaker noise or the wind noise or any other noise from the microphone signal. So that's one key reason to keep the sound qualities and distortions low. And of course, higher overload point is needed in music recordings also. In general, sound quality, low phase distortion is a key factor. Like I already said, noise cancellation, whether it's ambient noise cancellation, active noise cancellation, or echo cancellation, it always helps if the distortion and phase distortion is low. And frequency response is, of course, another key factor in MEMS microphones. For speech applications, telephony and speech UIs, the band from about 100 Hz to 8 kHz is usually wide enough. But then for audio video recording systems, you want to expand that to be, for example, from 50 to 15 kHz. And I'm running over my half an hour time, but I'll go through one more slide quickly. So, like I said earlier, contamination immunity is one place where there's room for improvement. Microphones are used in a variety of applications and conditions, and typically some sort of external protection is needed for the components in order to keep them safe and the device working well. And the bad thing about external protection, like meshes or membranes, is that they affect the microphone performance. They can lower the SNR by 1 or 2 dBs easily, and they also affect the frequency responses of components. There are some microphone technologies that address this contamination immunity and the need to improve it. For example, piezoelectric microphones and dual membrane microphones, capacitive microphones where there's a membrane on both sides of the backplate, and The idea there is that the gap between the membrane and the backplate is one of the vulnerable spots in a microphone where contamination can get, and having a membrane on both sides of the backplate makes it less probable that contamination gets there. Another place where improvement could be welcome is SNR. Even though the levels are really high now, the SNRs of MEMS microphones are still about 15 or 10 to 15 decibels worse than in these so-called normal scale studio microphones. In real life environments where the noise level is about 40 dBSPL or higher, such as a normal room in a residential home or something, MEMS microphones are okay because the ambient noise is so high. But if you go to a studio and do music recordings, then the ambient noise can drop down to 20 dBSPL, and then the noises of the components are not necessarily okay anymore. And the one last thing I want to mention is frequency response. So typically when a MEMS microphone is used in a device, it is connected to the air outside, so sound waves coming into the device through a sound channel, and the sound channels are typically not optimal things in terms of acoustics, and they cause resonances that limit the usable frequency ranges of MEMS microphones, and that's something that could use some improvement. Okay, that's it. I guess we have a few minutes for Q&A. Sorry for going over my time, but if you want to contact me for further discussion, then you can contact me at info@mosomic.com, or you can go and check my videos at youtube.com/mosomic.